So now we're going to solve some chapter 6 problems. So we learned that the work done is equals to force times the displacement and is equals to Fs cosine of phi, and this work done can be stored in terms of the kinetic energy, and this is your work energy principle, and your kinetic energy is nothing but the energy due to motion, which is mv squared. Okay, so you push your physics book, which is your heavy physics book, which is 1.2 meter along a horizontal table with the horizontal push is 10 newton, while the opposing force, which is your friction force, is 5.9 newton. So find the work done by the 10 newton force. So your work done is nothing but F dot S or Fs cosine of phi. In that case, your angle is 0, so cosine of phi, cosine of 0, which is 1, so you're left with Fs, and you have F, which is 10 newton, and it covers 1.2 meter distance. So your answer will be work done in 12 joules. Okay, so the next question is, what is the work done by the friction force? Okay, so the work done by the friction force so the friction is the opposite force. Okay, so the work done by the force of friction, so friction is always opposite to the motion. Okay, so the work done by the friction force is Fk, force with the friction force, S cosine of phi. So in that case, the object is moving in this direction and the friction force in this direction, so the angle is 180. So you have Fk S cosine of 180 degree. Okay, so your friction force is 5.9, so 5.9 multiplied by 1.2 cosine of 180, and cosine of 180 is minus 1. You calculate this, you will get minus 7.08 joules of work. So what will be the work done by the gravity? So the work done by the gravitational force is the work done by the gravity. Work done by the gravity is your work done by the gravity with the force which is along y, which is 0, because the work done force is 90 degree. So your force is work done by the gravity is 0. So what will be your total work? Then your total work done is total is your work done by the force plus the work done by the friction and plus the work done by the gravity. So this work is 12 minus 7.08 plus of 0, and you will get total work done, which is 4.92 joules. Okay, move to the next example. A 5 kilogram package slides 1.5 meter down a ramp that is inclined at the angle theta, which is this angle theta, 30 degree. The package slide down 1.5 meter under the influence of the gravitational and frictional forces. Find the work done by the force of friction. So we have calculated that the force of friction is Fk S cosine of 180 degree. Okay, because the force of friction and the motion are opposite direction. Okay, so we get the force of friction is 10 multiply by 1.5 cosine of 180 degree, so we get the work done is minus 15 joule. So work done by the gravity is the force or the weight along y. Okay, so the work done by the gravity is nothing but force along the y as cosine of phi. And what is the angle? Because this is making an angle theta. Okay, so the angle theta and the total angle and this angle, which is making this angle, this is 60 degree. So your angle will be your force or the work, your force or due to the gravity is nothing but the mg, which is 4.9, or you can write it as mg. S is your distance and cosine of 60 degree. This is your 60 degree. Okay, so you get 1.449 multiplied by 1.5 multiplied by cos 60 is 36.8 joules. Okay, then the work done by the normal force, so W done by normal force is ns cosine of phi due to normal force, and this is the angle between the motion. This is angle 60. Okay. Okay, so this is your angle, which is 90, normal force and the motion. So you have this is 90, this is your 60 angle. Okay, then you the 90, so cos 90 is 0, this work done is 0. So what is the total work done? Total is work done by the friction plus the work done by the force, which is gravity and the work done by the normal force, which is minus 15 plus 36.8 plus 0, which is nothing but 21.8 joules. Now moving towards your next example, the work done. So Steve pushes a car with the force this, and the displacement of the car is this. These are all vectors. How much the work done? So work done is nothing but the force times the displacement, 160 I minus 40 J dot 14I plus 11J. So you need to take a dot product. So dot product I multiply by I. So 160 multiply by 14 minus the 40 multiply by the 11. So dot product is just a number, and you calculate 1800 joules. Now so compare the kinetic energies of the two body in the three cases. Okay, so this is mass, this is moving in this direction, this is moving in this direction. So this has the kinetic energy K1, which is 1/2 m1 mv squared. Sorry, so K2 is 1/2 mv squared. So both has the same velocity v and the mass m, so their kinetic energies are equal. Now for this, your kinetic energy K1 is 1/2 mv squared, and for this kinetic energy 2 is 1/2 2mv squared. This m and this m will be cancelled out, so mv squared. So kinetic energy in that case is mv squared. So what is the relationship? So your kinetic energy of 2 is 2 times the kinetic energy of 1. Now for this the kinetic energy is 1/2 mv squared k1, and for this 1/2 m, and v is 2v squared, which is 1/2 m 4v squared. So we get 2 mv squared. Okay, so kinetic energy of this is the 4 times the kinetic energy of 1. This is the 4 time. Okay, now moving towards next example. So an object of 6 kilogram has the kinetic energy of this at a point A and kinetic energy of 7.50 at B. What is the total work done by moving from point A to B? So the work done is nothing but the change in kinetic energy. So change in kinetic energy at B, kinetic energy at B minus the kinetic energy at A. So we are given that point 7.50 minus 2.5, we get 5 joules. Now the next problem. Okay. The tractor pulls a sled loaded with wood. Total weight. So the total weight is of these two things, tractor plus the sled. Okay, a distance of 20 meter. This is your S, this is your W. The total work done by the sled is 10 kilojoules. Suppose that the sled's initial speed, this is your VI or initial. What is the speed of the sled after it moves 20 meter? So we need to find V2. This is V1. Okay, so we're going to apply our work energy theorem, which is the work done total is equals to the change in kinetic energy, which is the kinetic energy at 2 minus the kinetic energy at 1. Okay, so we are given by the work done. So work done is given by the total, okay, which is 10,000 joules, and you have 1/2 mv2 squared minus 1/2 mv1 squared, and we are given by the initial speed, but we don't have the mass, but we can calculate the mass from the weight. So W is equals to mg, so m is W divided by g, so we get 400 divided by 9.81, so we get 1500 kilogram. So now we have the mass. So the work done is, so we need to calculate V2. For this we have W plus 1/2 mv1 squared. So V2 is nothing but 2W plus plus mv1 squared divided by the m and the square root. So your V2 is nothing but 2w plus mv1 squared divided by m. So when we substitute the value, we get velocity 4.2 meter per second. So this is how we calculate the velocity. Moving towards the next problem. Next part. A tractor driver is constant speed sled loaded with the firewood. There is a friction between the sled and row. Find the total work done on the sled after it moves to a distance of 20 meters. So it's moving with a constant speed, which means the rate of change of kinetic energy is constant because the change in kinetic energy is K2 minus K1 is nothing but 1/2 mv2 squared minus 1/2 m1v1 squared. So both is moving with the same velocity, v1 equals to v2, so this goes to 0. So the change in kinetic energy is 0, so work done is the change in kinetic energy, which is 0 in that case. Okay, so the last problem of this work and kinetic energy is this. A block of mass m1 kilogram is released from the height, okay, above the surface of the table, thus making an angle inclined theta with 30 degree. This is your 30 degree as shown in the figure. This slide down. The force of a 2 Newton force of kinetic friction resists the downward motion. So the kinetic friction force is 2 Newton. Determine the speed of the block when it reaches the bottom. So determine the speed at the bottom. So it start with some initial velocity and it start with the rest, because it start with the rest, so its initial velocity is 0. Okay, its mass is 1 kilogram and the height is 1.5 and it's making an angle. Okay, so the distance, this distance from this distance, take this as s. Okay, so if you see this is the right angle triangle. Okay, and in the right angle triangle, sine theta is nothing but sine theta is perpendicular over the hypotenuse, and perpendicular is 1.5 is this h, okay, and hypotenuse is this in the triangle is this, so s, and the angle is 30 degree 5 s, so your s is 1.5 divided by sine 30 degree, which is 3 meters. So your force of friction is given and we need to find out the velocity v2. So your work done is stored in the change of kinetic energy. This is your total work done. Now the work done is the work done by the gravity, the work done by the friction, and the work done by the normal force. This is what we see in the previous problem. So for a total work, you need to calculate these values, and the change in kinetic energy is nothing but 1/2 mv2 squared minus 1/2 m1v1 squared. So because it's starting from 0, so this goes to 0. So your normal work and the distance between the normal work, angle between the normal force and the distance is 90, so your normal work is 0 as well. So we left with this. So the angle between the weight and the displacement is 60 degree, which is this angle. So your Fs cos 60 degree plus your Fks cos 180 degree, which is the frictional work, and you have V2 squared. Then your F is nothing but your weight, which is W, force of gravity, which is mgs cosine 60 plus your Fk, which is given 2 Newton. Okay, so Fk is given, S is we have calculated, and cos 180 is minus 1, so we get 1/2 mv2 squared. Okay, so what we have, V2 is, it's 2 mgs cosine 60 plus 2 Fks cosine 180 divided by the m, and then you have to take the square root on both sides. So you get V2 is 2 mgs cosine 60 plus 2 Fk cosine 180 degree divided by the m. So your V is 4.2 meter per second. So this is how you calculate the velocity. Just put the values, because it's 1 kilogram, and just substitute the values. So you will get the 4.2 meter per second at this end. So at this end, its velocity is 4.2 meter per second. Okay, now we're going to solve some problems related to springs. Okay, so if you are given by a force and force position versus the force graph, so your work is nothing but the area under the curve. If you have a curve, this is the area under the curve, and your work done is nothing but the integral from 0 to any point x, the force applied time dx. Okay, so when you have springs, your force is kx, which is the Hooke's law. It says that this is your force, then your work is nothing but 0 to x is kx dx, and you solve this integral, you will get 1/2 kx squared, because k is constant. Okay, and then your work done in moving the spring from equilibrium position to some another position like 0 and x, okay, from this position to this position, and this is your initial position, this is your final position. So your work done is stored is nothing but 1/2 kx1 squared minus 1/2 kx2 squared. So this is the work done by the spring. Work done by the spring. Okay, then you have the rate of change of work, which is your power. This is your average power. rate of change of work. Then you have instantaneous power, which is nothing but dw divided by dt, and you can find work by the force times the velocity, which is the product of force and velocity. If you're finding some problem on these concept, you can review the video of chapter 6 concept review. So now we're going to solve some problems. So if you require 49 joules of stretch to work an ideal spring of 1.4 meters from the equilibrium, what is the value of your spring constant? Okay, what is the value of your spring constant in that case? So your work done, your applied your work is by the force applied is given by 49 joules, and you move from equilibrium position 0 to x equals just 1.4 meter. So your work done by the spring is nothing but 1/2 kx1 squared minus 1/2 kx2, okay, or the change in the work done, which is 1, okay, which is x2 minus x1, change in the work. So this is 0, so you get 1/2 k x2 squared. So you have this position, so k is 2w applied force applied divided by x2 squared, and when you substitute x2 is 1.4, the work done is 49. When you put the value, you will get 50 Newton per meter, the spring constant k. Okay. So a block of M is attached to a spring as shown in the figure. A force of 300 Newton is required to move a block from point x equal to 4 centimeters to equilibrium x equals to 0. Find the spring constant. Okay, so it moves from, so your force is 300 Newton, so your force applied is kx, so your k is force applied divided by the x, and the x is the change of the position. Okay, so this is f and the position is 4. The force is 300 Newton, so 300 Newton divided by 4 centimeter, which is nothing but 0.04 meters. Okay, so you will get 7500 Newton per meter. Okay. Now the next is the work done by the spring. Work done by the spring. So the work done by the spring from moving from stored in the work done, then 1/2 kx1 squared minus 1/2 kx2 squared. Okay, so the work done by, so x is 0, so this was 0, so work done by the spring is 1/2 kx2 squared, which is nothing but, you put the value of 0.04 squared, k is 7500 and 1/2, so you will get minus 6 joule of work done by the spring. So if the spring is released from the rest, okay, what is the speed of the block at x equals to 0? Okay, so in that case, your initial position is this point, your final position is this point. Okay, so this is your 0.04 meters, this is your 0. Okay, then it starts from rest, then its v1 is 0. Okay, and we need to find out what is the speed at this point. So we apply our work energy theorem. So what is your work? work is nothing but the change in kinetic energy, which is nothing but 1/2 mv1 squared minus 1/2 mv2 squared. Okay, so start from rest. So this is 2 and 1, sorry. So it starts from rest, so this point is goes to 0, and your work done by the spring is 1/2 kx1 squared minus 1/2 kx2 squared is equals to 1/2 mv2 squared. So this point is 0, so half and half will be cancelled out, and your v2 is nothing but k x1 squared divided by m v squared, and then you take the square root on both sides, so your v2 will get k x1 squared m. And when we substitute the value, k is 7500, x1 is 0.04 divided by the mass, which is 0.1. Then you take the square root, and then we calculate the velocity, which is 10.9 meter per second. Okay, so now this problem. So you are given by a graph, the force is acting on the object varies as figure below. The work done by the force on the object is moved from 0 to 8 meters. Okay, so we said that work is nothing but the area. So from 0 to 8, so this is your area. So it is a triangle. Okay, so area of a triangle, which is nothing but 1/2 base times the height, and your base is 8 and your height is 6. So 1/2 6 multiplied by the 8, so you will get 24 joules of the. So now you calculate the work done from point x8 to x12. Okay, so if you see this, this is the area of a triangle. So work is area, and area of a triangle is 1/2 base times the height. So your base is this, which is 8 to 12 is 4, and your height is this, which is I think 3, so which is -3. So 1/2 4 times the -3 is 6 joule with a minus sign. Okay, now at x equals to 0, the speed of the object is this. Find its speed at x equals to 12. Okay, so we can find speed by using the work energy principle. So work of total is equals to the change in kinetic energy. And change in kinetic energy is 1/2 mv2 squared minus 1/2 mv1 squared. So v1 is given 5 meter per second, x is 0. Okay, so this is the total journey, and this is divided into, so the work done from 0 to 12 is 1/2 mv squared minus 1/2 mv1 squared. So your work done from 0 to 12 is divided into two sections, 0 to 8 plus 0 8 to 12, and we have calculated that work. 1 half mv2 squared minus 1 half mv1 squared. So this work we calculated 24 minus 6 equals to 1 half mv2 squared minus 1 half mv1 squared, and your v2 is nothing but 18 multiplied by 2, no 18 plus 1 half mv1 squared, 1 half mv2 squared, and then we multiply by 2 and divided by m, then your v2 will be like 36 plus m v1 square divided by your m. Okay, and when we substitute and then we take the square root of it, and then we will calculate the velocity, it will be 9.9 meter per second. Okay, so you have 36. You can calculate your mass is 0.5 kilogram and your v1 is 5 meter per second. So you have all the data, you can calculate, put in the value, and you will get v2 is 9.9 meter per second. Now the next example is given by a force acting on the object. Our next example is this: for you are given by a function force and you need to calculate the work done from -1 to 1 plus 2. Okay, -1 to +2. So the work done by the force is nothing but from x -1 to x2 is the force times the element. So your force of x is given, which is nothing but -1 to x equals to 2, which is 14x minus 3x squared, which is the x. So we will calculate these integrals. So this is x integral, which is 14x squared divided by 2 minus 3x3 divided by 3, and your value is from -1 to 2. So you put value of 14, 2 squared divided by 2 minus 2 cube divided by 3. So first, then the minus 14 minus 1 squared minus 3 minus 1 cube divided by 3 divided by 2. So now when we calculate these, we get 20 minus 8, which is 12 joule of work done by that force. Okay, so the next problem is related to the power. So a 700 Newton monkey climbs a 10-meter vertical rod at a constant speed in 8 seconds. Constant speed in 8 seconds. What is your average output power? Okay, so the power is nothing but delta W divided by delta T. Okay, so this is the work done. So what is the work done by this 70 kilogram monkey to climb 10 meter? Okay, so this work done is done by the gravitational force. Okay, so the work done will be the gravitational force. So work done is Fs cosine of phi, and the force in the downward direction, and the monkey is covering distance in the upward direction. So your angle is nothing but 180, and your force is your weight mg s cosine of 180 degree. So your work done is 70 multiplied by 9.8 multiplied by 10 meters, then the cosine of 180 degree. So your work done is 7,000 joule. Okay, this is the work done by the gravity. Okay, so what is your power now? So power is work done divided by your time, which is 875 watt. Okay, so what is the instantaneous power? So for instantaneous power, we have the power is F dot V. Okay, so your F dot V, and your V is nothing but D divided by T, and which is 10 divided by 8, which is equals to 1.25 meter per second. Okay, so your P is F dot V, which is FV cosine theta, and theta both are in the same direction, so angle is 0. So you will get P is mg, which is 700 multiplied by 1.25, and your power is 875 watt. So both of your power is equal, which is this and this. Your average power and instantaneous power are equal. Now moving towards the next example. So power of a car engine is this. If the car accelerates from rest with negligible air resistance, what is the work done by the car engine after 7 seconds? Okay, so your power is nothing but the rate of change of work, and your work is P into delta T. Your power is 628 multiplied by 746, because 1 horsepower is 746. Okay, times your time, and you will get 3279 kilojoules of work. Next example is a sports car of mass 1500 kilogram accelerate from rest, which is the initial velocity 0, and rest to 100 kilometer per hour in 5 seconds. What is the power? Okay, so power is the rate of change of work divided by the rate of change of work. So your work, which is nothing but the change in kinetic energy, which is nothing but 1/2 mv2 squared minus 1/2 mv1 squared. Your v1 is 0, your v2 is 100 kilometer per hour, which is nothing but 100 multiplied by 1000 divided by 3600. Okay, so this is your velocity, and the time is 5 seconds. Okay, so this is 0, so you will get 1 half 1500 into 1100 multiply by 1000 divided by 3600 squared. So you will get 5787 10 raised to power 10 raised to power 5 joules, and your power is nothing but the work done divided by the time, which is 5.787 10 raised to power 5 divided by the 5, which is equals to 1.157 10 raised to power 5 watt. So you can convert this power into horsepower. So your horsepower is nothing but 1.157 10 raised to power 5 divided by 746, which is 155.14 horsepower. So you will get the power. Okay.